Listen to the room around you, not actively, just let it in. The low hum of something electrical, the distant sound of traffic or wind, or a conversation somewhere beyond a wall. The small creaks and sighs of the building settling on its foundations. Even in the quietest room you have ever sat in, there is noise, there is movement, there is energy doing things, transferring, converting, dissipating, flowing from one form into another. This is how the universe has always felt to us. Busy, dynamic, full of things happening, stars burning, galaxies rotating, black holes pulling in everything that wanders too close, neutron stars spinning hundreds of times per second, sweeping beams of radiation across the cosmos like the beam of a lighthouse gone mad. The universe, from where we are sitting, appears to be a place of relentless, extraordinary, almost overwhelming activity. And it is, right now. But this is not a permanent state of affairs. What we are experiencing, this luminous, energetic, star-filled, galaxy-spanning moment, is not the default condition of the universe. It is a brief interlude, a parenthesis in a story whose first and last chapters are both written in silence and cold. We happen to have been born during the middle of the story, in the warm and noisy chapters, and it is natural to mistake the middle for the whole. The universe is dying, not quickly, not dramatically, not in any way that would produce headlines or require an evacuation plan. It is dying in the slowest, most patient, most methodical way imaginable, through a process so gradual that the word gradual fails it almost as completely as the word slow fails a glacier. It is dying through the relentless and irreversible leaking away of usable energy, through the cooling of everything that is warm, through the dimming of everything that shines, through the grinding down of every structure that exists into the featureless, cold, eventless equilibrium that thermodynamics has been demanding since the moment the universe began. This process has a name. Physicists call it the heat death of the universe. But that name is misleading because the end state is not hot, it is cold. It is the coldest possible thing. A universe in which no temperature differences exist anywhere, in which no work can be done, in which nothing further can happen. It is, in other words, a universe that has gone quiet. This is the story of how that happens, how the busy, noisy, brilliant universe we inhabit will, over time scales that make the age of the cosmos look like a momentary flicker, slowly and irreversibly wind down, how one by one its lights will go out, how its last structures will dissolve, how the laws of thermodynamics, laws that govern every process in nature from the burning of a candle to the fusion of hydrogen in a stellar core, will, given enough time, reduce everything to nothing worth having. It is a long story. It is, in fact, the longest story there is. And it begins with a concept that most people think they understand, and almost nobody truly does. The second law, entropy. There is perhaps no concept in physics that is more frequently cited, more routinely misunderstood, and more genuinely profound than entropy. It appears in everything from discussions of thermodynamics to information theory to the arrow of time to the ultimate fate of the universe. And it begins, as most great ideas do, with something ordinary. Think about a cup of tea. You make it hot, you leave it on the table. You come back an hour later and it is cold. The heat has dispersed into the surrounding room. The tea and the room have reached thermal equilibrium. They are the same temperature, and no further heat flows between them. Now ask yourself, why does this never happen in reverse? Why does the cold tea never spontaneously gather heat from the cooler room around it, growing hotter while the room grows colder? The laws of energy conservation, the first law of thermodynamics, would not be violated. Energy would be conserved. The same amount of heat that left the tea to warm the room could, in principle, leave the room and warm the tea back up, but it never does. The reason is the second law of thermodynamics. In any spontaneous process, the total entropy of a closed system tends to increase or, at best, stay the same. Entropy is, loosely speaking, a measure of the number of ways the microscopic constituents of a system can be arranged while still producing the same macroscopic appearance. Hot tea in a cool room has a specific, relatively ordered microscopic arrangement. The fast-moving molecules are concentrated in the cup, the slower ones distributed throughout the room. That distribution can be realized in relatively fewer ways. Tea and room at the same temperature has a vastly greater number of microscopic arrangements that all look identical from the outside. It is overwhelmingly more likely, so overwhelmingly more likely that the reverse has never been observed in the history of science, that the system will evolve towards the higher entropy state. The second law is not a law in the sense of something imposed from outside. It is a statement about statistics, about the crushing, insurmountable weight of probability. There are more ways for things to be disordered than for them to be ordered, and so disordered is where they almost always end up. Ludwig Boltzmann, the Austrian physicist who put the second law on its modern statistical footing in the 1870s and 1880s, understood this with a clarity that his contemporaries found at best difficult and at worst offensive. His statistical interpretation of entropy was attacked by prominent physicists who refused to accept the atomic theory of matter on which it rested. Boltzmann spent decades defending his ideas, often in a state of profound depression. He died by his own hand in 1906, just 2 years before the experimental confirmation of atoms would vindicate him completely. The formula for entropy, S equals K, times the logarithm of W, where K is Boltzmann's constant and W is the number of microscopic configurations, is engraved on his tombstone in Vienna. It is one of the most important equations in the history of physics, and it is the equation that seals the universe's fate. The arrow of time. The second law does something else. Beyond explaining why tea goes cold, it does something philosophically extraordinary. It gives time a direction. Every fundamental law of physics, Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, quantum mechanics, is at its core symmetric in time. The equations work equally well running forward or backward. A film of 2 billiard balls colliding looks equally physical whether played forward or in reverse. A film of planets orbiting the sun looks equally physical in either direction. At the level of individual particle interactions, there is no arrow, no preferred direction, no fundamental distinction between past and future. And yet we experience time as having an arrow, a relentless one-way current. The past is fixed and the future is open. Causes precede effects. Broken eggs do not unbreak. The dead do not come back. The cold tea does not spontaneously reheat. The second law, and only the second law, provides a physical basis for this asymmetry. Because entropy increases in one direction and not the other, that direction becomes forward. The arrow of time on this understanding is not a fundamental feature of the laws of physics. It is an emergent consequence of the fact that the universe began in a state of extremely low entropy, the Big Bang, and has been moving toward higher entropy ever since. The past feels fixed because it is lower entropy. The future feels open because higher entropy states are more numerous and therefore statistically accessible. There is something quietly staggering in this. The reason you remember yesterday, but not tomorrow. The reason a glass falling to the floor shatters and does not reassemble. The reason you grow older and not younger. The reason every fire eventually dies and every star eventually goes out. It is all the same reason. It is all the second law. It is all the universe flowing with absolute statistical inevitability from the extraordinary low entropy spark of the Big Bang toward the maximum entropy stillness that lies unimaginably far in the future at the other end. We are living on the downslope. We always have been. The question is just how long the slope is. The Stelliferous Era. What we have now, before following the universe into its dark future, it is worth pausing to appreciate what we currently have. Because what we currently have is, by the standards of the universe's long history, genuinely extraordinary. We live in the Stelliferous Era, the age of stars. It began roughly 100 million years after the Big Bang, when the first generation of stars ignited in the primordial darkness, and it will continue for roughly another 100 trillion years. Though its peak, the moment of maximum cosmic star formation, passed roughly 10 to 11 billion years ago and will never return. Right now, across the observable universe, approximately 2 trillion galaxies are shining. Each one contains hundreds of billions to trillions of stars. Each star is a gravitational pressure cooker in which hydrogen nuclei, single protons, are being forced close enough together that the strong nuclear force can bind them into helium, releasing energy that has been powering the universe's biology, geology, chemistry, and physics for billions of years. The Sun alone outputs roughly 3.8 times 10 to the power of 26 watts. That is a number so large it resists any useful comparison. If you collected all the energy humanity has ever generated in its entire history, every lump of coal, every barrel of oil, every nuclear reaction, every wind turbine, it would not be enough to power the Sun for a single second. And the Sun is an ordinary, middle-of-the-road, entirely unremarkable star. This is the universe as it currently stands. Incandescent, productive, generating energy on a scale that beggars any human frame of reference. But every star in the sky is burning through a finite supply of fuel. Every nuclear reaction in every stellar core is consuming hydrogen that cannot be replaced. The reservoir of raw material for star formation, the cold molecular hydrogen clouds that collapse under gravity and ignite, is being steadily drawn down. The universe is spending its inheritance. And the inheritance, for all its immensity, is not infinite. The Stelliferous Era will end. The question is what comes after, and after, and after that. The first lights go out. The first stars in the universe were not like the stars we see today. They formed in the first few 100 million years after the Big Bang. from a universe that contained only the elements produced in those first few minutes of nucleosynthesis: hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no iron, no silicon. None of the heavier elements that color the spectra of modern stars and form the rocky planets around them. These first stars, known to astronomers as population 3 stars, formed from primordial gas that had never been enriched by a previous generation of stellar death. Without heavy elements to carry heat away from collapsing gas clouds, without the cooling that carbon and oxygen provide through their emission of infrared radiation, these earliest stars formed large, very large. Some of them may have been hundreds of times more massive than the Sun, and massive stars burn fast. A star 100 times more massive than the Sun lives for only a few million years before exhausting its fuel and dying in a catastrophic supernova, scattering the heavy elements it has forged in its core across the surrounding space, seeding the universe with the raw material for a new generation of stars. Those supernovae, the deaths of the first generation, were among the most energetic events in cosmic history, and they were the beginning of the end of stellar simplicity. The universe, enriched with heavy elements for the first time, could now form smaller, longer-lived stars. The first galaxies began to coalesce. The cosmic web of structure began to grow. The universe was, in a sense, growing more complex through its own deaths. This is one of the more poignant ironies of cosmic evolution. Stars die so that better stars can be born. The heavy elements in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, were made inside stars that died billions of years ago, scattered by their deaths, incorporated into new molecular clouds, and eventually folded into the solar nebula that became our Sun and its planets. You are, literally, the recycled ash of dead stars. But the recycling is not indefinite. With each generation, some fraction of the available hydrogen is locked away in the compact remnants of stellar death. White dwarfs, neutron stars, black holes. That hydrogen cannot form new stars. The supply for future star formation is not replenished. It only shrinks. The most massive and luminous stars, the spectacular blue giants that dominate the light of young galaxies, are already gone. They burned for millions of years and died. The Sun has about 5 billion years left. After that, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, cooling sphere of carbon and oxygen the size of the Earth, no longer fusing anything, simply radiating its stored heat into the surrounding space. And the longest-lived stars, the dim red dwarfs, will burn for up to 100 trillion years, patient and persistent beyond all reckoning, before finally cooling to dark. When the last red dwarf goes cold, the Stelliferous Era is over. The universe goes dark. What the dark looks like. Picture the universe after the last star has gone out. It is not empty. Emptiness implies the absence of everything, and there is still a great deal of matter. Most of it, by mass, left in the universe. But none of it is burning. None of it is shining. None of it is generating any significant new energy. What remains is a vast and dark collection of cold objects, drifting through a universe that has grown so large through billions of years of continued expansion, that the distances between things are now almost incomprehensibly greater than they are today. There are white dwarfs, hundreds of billions of them in our galaxy alone, the cooling remnants of sun-like stars and red dwarfs that ran out of fuel long ago. They are no longer white. They have been cooling since their formation, and the oldest of them are now fading from white to yellow, to orange to red, to the deep infrared that no human eye could detect. Given enough time, far more time than the universe has yet existed, they will cool to the point where they emit no light at all. They will become black dwarfs, cold, dark, inert balls of crystallized carbon and oxygen, roughly the size of the Earth, roughly the mass of the Sun, floating invisible in the dark. Nothing to see, nothing happening. There are neutron stars, the ultra-dense remnants of the most massive stellar deaths, objects so compressed that a teaspoon of their material would weigh 100 million tons here on Earth. They too are cooling. The youngest neutron stars are hot enough to emit X-rays. The oldest are cold enough to touch. Cold by stellar standards anyway, at just a few thousand degrees. Given enough time, they too will cool toward absolute zero. They will join the black dwarfs in the silent inventory of the dark. There are black holes. The supermassive black holes at the centers of former galaxies, containing masses equivalent to millions or billions of suns. The stellar mass black holes scattered throughout galactic space, each one the remnant of a star that died in a supernova billions of years ago. They are, of all the objects in this dark universe, the ones most readily visible. Not because they emit light, but because they distort space around them, and because, as Hawking showed, they are very slowly radiating. And then there are the lesser things. Brown dwarfs, bodies too small to ever ignite nuclear fusion, failed stars, warm and dim, cooling in the dark. Rogue planets, worlds that were flung from their solar systems by gravitational interactions with other bodies, now traveling alone through the void on no particular errand. Asteroids and comets and the rubble of dismantled planetary systems, drifting in the cold. The universe, after the stars, will be a very dark and very quiet place. But it will not yet be at rest. Not for a very long time. The slow unraveling, degenerate matter and proton decay, the era after the stars, the Degenerate Era, as Fred Adams and Greg Laughlin named it, is defined by the slow cooling and potential decay of the white dwarfs, neutron stars, and brown dwarfs that populate it. These objects are held up against gravity not by the thermal pressure of hot gas. That era is over. But by quantum mechanical degeneracy pressure. Electrons in white dwarfs, neutrons in neutron stars occupy discrete quantum energy states, and the Pauli exclusion principle, which forbids two fermions from sharing the same quantum state, produces an outward pressure that holds these objects against gravitational collapse. This pressure is not thermal. It does not diminish as the object cools. A white dwarf will remain stable essentially forever, as long as nothing disturbs it, regardless of how cold it becomes. This is why black dwarfs, once formed, would be extraordinarily stable. They are quantum mechanical objects, not thermal ones. Gravity cannot collapse them further. There is nothing to burn. They simply sit there, cold, dark, inert, stable, unless protons decay. The proton, the nucleus of the hydrogen atom, the fundamental building block of ordinary matter, appears within the standard model of particle physics to be essentially stable. Its predicted lifetime within that framework is so long as to be effectively infinite, but many extensions of the standard model. particularly the grand unified theories that attempt to unify the strong, weak, and electromagnetic forces into a single framework, predict that protons should eventually decay, not rapidly and not in a way detectable on any human timescale, but over spans of time measured in powers of 10 to the 30s, 40s, or beyond. The experimental lower bound on the proton lifetime, established by enormous underground detectors in Japan, the United States, and elsewhere, currently sits above 10 to the 34 years for the most commonly predicted decay mode. But decay modes predicted by more complex GUT models have longer predicted lifetimes, as yet unconstrained by experiment. If the proton does decay, if it has a finite lifetime somewhere in the range that theoretical physics considers plausible, then the implications for the Degenerate Era are stark. Over time scales of perhaps 10 to the 37 or 38 years, every proton in every black dwarf, neutron star, and brown dwarf would eventually decay, one by one, each decaying proton releasing a tiny amount of energy, a brief, faint flicker of warmth in the surrounding cold, before converting into lighter particles that then themselves decay or annihilate. The solid crystalline structure of a black dwarf would slowly dissolve, not from the outside in, but from within, proton by proton, over time scales so immense that the comparison with any previous number in this story is almost pointless. The cold, dark remnants of the universe's stars would not merely cool toward absolute zero and sit there forever. They would evaporate, and the universe would become, if proton decay occurs on any of the predicted timescales, a place containing essentially no ordinary matter at all. No atoms, no molecules, no chemistry, no planets, no rocky surfaces, no familiar material of any kind. Just photons, neutrinos, electrons, positrons, the lightest particles, unable to decay further, drifting through an enormously expanded void. And the black holes. The black hole era. If protons decay, the Degenerate Era ends and the black hole era begins. If protons do not decay, if the proton is genuinely stable, then the transition is more gradual, the black dwarfs and neutron stars persisting longer. But either way, there arrives a point at which the dominant objects in the universe are black holes. Black holes are the most durable structures the universe produces. They require no fuel. They require no internal processes. They are, in a sense, pure geometry, regions of space-time so severely curved that the curvature is self-sustaining, requiring nothing from outside to maintain itself. A black hole that forms today and is left entirely alone will, in the framework of classical general relativity, last literally forever. But the universe does not operate in the framework of classical general relativity alone. And when quantum mechanics is brought into the picture, even black holes are mortal. Hawking radiation, the quantum mechanical emission of particles from the vicinity of a black hole's event horizon, causes every black hole to slowly lose mass and energy. The mechanism, discovered by Stephen Hawking in 1974, arises from the quantum behavior of fields near the extreme space-time curvature of the horizon. It produces a thermal spectrum of particles, as if the black hole's surface were glowing with a temperature that is inversely proportional to its mass. For large black holes, this temperature is extraordinarily small. The supermassive black hole at the center of the Milky Way, Sagittarius A star, with a mass of roughly 4 million solar masses, has a Hawking temperature of about 10 to the minus 14 Kelvin. That is 100 million times colder than the cosmic microwave background radiation currently permeating the universe. Hawking radiation from Sagittarius. A star is, right now, completely swamped by the energy it absorbs from the surrounding universe. But the universe will not always be as warm as it is now. As it expands and cools over billions of years, the temperature of the cosmic microwave background drops. Eventually, in the far future, the background temperature of the universe will fall below the Hawking temperature of even the largest black holes. At that point, black holes will begin to lose more energy than they gain. They will begin to shrink. Slowly at first, barely noticeably. A stellar mass black hole loses mass so slowly to Hawking radiation that its current shrinkage rate is far smaller than anything detectable. But the process is relentless and cumulative. And crucially, as a black hole loses mass, its temperature rises. A smaller black hole is hotter, radiates faster, loses mass faster still. The process accelerates. The final moments of a black hole, when it has shrunk to the mass of a small asteroid or a mountain or a large boulder, are explosive. The temperature soars. The radiation output spikes. The last fraction of the black hole's mass is converted to a brilliant burst of high-energy particles and radiation in an event that is, briefly, extraordinarily energetic, and then silence. For stellar mass black holes, the evaporation time is roughly 10 to the 67 years. For the supermassive giants at galactic centers, with masses billions of times greater, the evaporation time stretches to around 10 to the 93 or 94 years. 10 to the 94 years. This number cannot be compared usefully to anything in ordinary human experience. It is not merely large. It is large in a way that places it in an entirely different category from any number that appears in ordinary science, engineering, or daily life. The age of the universe is 10 to the 10 years. The time until the last star burns out is 10 to the 14 years. The proton lifetime is around 10 to the 34 to 38 years. Each of these numbers is itself incomprehensible, and they each fall further and further short of 10 to the 94. When the last black hole evaporates, when the final supermassive remnant of a galactic center releases its last burst of Hawking radiation into the surrounding void, the black hole era will be over, and the universe will face the last and longest of all its eras. The dark era. After the black holes, after the protons, if they decay. After every structure that physics can currently describe has either evaporated, decayed, or cooled to the point of stillness. What remains? The answer is both specific and profoundly anticlimactic. Photons. The photons released by every nuclear reaction in every star that ever burned, every proton that ever decayed, every black hole that ever evaporated. All of them still traveling through an expanding universe, their wavelengths stretched by that expansion to extraordinary lengths, their energies correspondingly diminished towards zero. They carry energy, but it is uniformly distributed, infinitely dilute, capable of doing no useful work. Neutrinos, the ghostly, almost massless particles that interact with matter so weakly that a light year of solid lead would stop only half of them. They pass through ordinary matter essentially without interaction. They cool, they drift. They are, at this late stage of the universe, the most common massive particles in existence, and they are doing nothing. Electrons and positrons. the antimatter counterpart of the electron, the positron should long since have annihilated with electrons in the hot early universe. And most did. But in the cold, dark, vastly expanded universe of the dark era, electrons and positrons are separated by distances so enormous that they almost never meet. They drift, cool and lonely, through the void, and the void itself. Space continues to expand, driven by the dark energy that constitutes the bulk of the universe's energy content. The distances between particles, already incomprehensible, grow larger and larger. The universe becomes steadily more diffuse. The average density of particles approaches zero. The average temperature approaches absolute zero. Not from above, closing in. From above, asymptotically, with the universe never quite reaching absolute zero, but approaching it with the slow inexorability of a limit in calculus. This is the state thermodynamicists call maximum entropy, the heat death, the equilibrium. The condition in which no temperature differences exist anywhere, in which no energy can flow from hot to cold, because nothing is hotter than anything else, in which no work can be done, no structure can form, no information can be processed. It is a universe in which nothing happens, not nothing as in very little, nothing as in an absence so complete that the word nothing itself seems inadequate. This is what the second law of thermodynamics has been driving toward since the very first moment of the Big Bang. This is the destination that every burning star and every crashing galaxy and every spinning neutron star has been moving toward all along, without deviation and without the possibility of deviation. The laws of thermodynamics do not compromise. They do not make exceptions. They are not negotiable. The universe will reach this state. The only question is when. And the when, given the timescales involved, is not a pressing concern for anything alive today. The quantum long shots. But here, at the very edge of physics, in the uttermost depths of the dark era, with everything we know about the universe suggesting that nothing further can happen, something peculiar must be acknowledged. Quantum mechanics is not done. The vacuum of space, even in the most extreme state of thermodynamic equilibrium, is not truly inert. Virtual particles continue to flicker in and out of existence, as they have always done, because the Heisenberg uncertainty principle does not care about the age of the universe. Quantum fields continue to fluctuate, and quantum fluctuations, given enough time, can occasionally produce configurations of matter that would, by any classical reckoning, be impossible. This was the insight of Ludwig Boltzmann applied to the quantum realm. In a system at equilibrium with an infinite amount of time ahead of it, rare fluctuations are not merely possible, but inevitable. Fluctuations so rare that they have never occurred in the history of the observable universe will, given infinite time, eventually occur, and then occur again and again. In a universe of infinite duration, even the formation of a complex, organized structure, by pure chance, from the random jostling of the few remaining particles, becomes not merely possible, but certain to happen eventually. The time scales are themselves almost beyond mathematical expression. The spontaneous fluctuation of a single protein molecule from the surrounding particles would take on the order of 10 to the power of 10 to the 20 years, a number so recursive it barely qualifies as mathematics. A human brain, the kind of spontaneous organized fluctuation philosophers call a Boltzmann brain, would take incomparably longer. Whether these fluctuations represent any meaningful kind of experience, any genuine moment of consciousness in an otherwise dead universe, is a question that physics cannot answer. They would be isolated in time and space, surrounded by the void, with no context, no history, no future. A single flicker of organized matter in the dark, gone almost as soon as it appeared. But they would be something in a universe that otherwise contains nothing. Whether that is comforting or terrifying is not a question for physics. The exceptions, or what might save us. It would be dishonest to present the heat death as the only possible future without acknowledging the alternatives. The possibilities that current physics does not rule out, and which would change the story entirely. The heat death depends on dark energy behaving as it currently appears to behave, as a cosmological constant, a fixed energy density of empty space that drives an accelerating but steady expansion. If dark energy remains constant, the universe expands forever, cools forever, and the heat death is the inevitable endpoint. But dark energy might not be constant. If dark energy strengthens with time, if its density increases as the universe expands, rather than remaining fixed, then the expansion of the universe does not merely accelerate, it accelerates without limit. Galaxies are torn apart, solar systems are torn apart, planets are torn apart, atoms are torn apart. The fabric of space-time itself is shredded at every scale in what physicists call the Big Rip, a catastrophic end to the universe that arrives not in the quiet of thermodynamic equilibrium, but in the violent disintegration of everything, right down to the atomic and subatomic scale. Current observations do not prefer the Big Rip. The data are consistent with a cosmological constant, but they do not rule out a slowly increasing dark energy, and the distinction matters enormously for the universe's fate. If dark energy weakens with time, if it is not a constant but a dynamic field that can diminish, then the expansion might eventually slow, halt, and reverse. A contracting universe would grow hotter as it compressed, heading toward a big crunch. The time reverse of the Big Bang, a final compression of all matter and energy into a singularity at the end of time. The heat death would be preempted by a catastrophic collapse. Again, current observations do not prefer this, but they do not conclusively exclude it. And if the universe has the kind of cyclic structure proposed by Paul Steinhardt, Neil Turok, or Roger Penrose, if the end of our cosmic cycle is in some mathematical sense the beginning of the next, then the heat death is not truly the end. It is a transition, a reset, a new cycle beginning precisely where the old one becomes indistinguishable from a starting condition. The quiet death may be followed by a birth. We do not know. What entropy means for us now. All of this, the heat death, the dying stars, the evaporating black holes, the quantum silence, might seem remote, and in one sense it is. The timescales are so vast that no living thing, no civilization, no planet will endure anywhere near long enough to witness the later stages of this story. But in another sense, the second law of thermodynamics is not remote at all. It is operating right now, on you, on everything around you. Every time you eat a meal, you're taking in low entropy food, structured, organized matter with energy stored in chemical bonds, and converting it into higher entropy waste heat and carbon dioxide and water. Your body is an entropy processing machine. It maintains its own low entropy, its own remarkable organization, by exporting entropy to the surrounding environment at a greater rate. You stay ordered by making the universe, on balance, more disordered. Every time something burns, a candle, a fire, a star, it is converting organized chemical or nuclear energy into diffuse heat that spreads into the surrounding environment and cannot be fully recovered. Every time a machine runs, friction converts organized kinetic energy into disordered thermal energy. Every time a wave breaks on a beach, the organized kinetic energy of the wave is converted into the disordered thermal energy of warmer water and scattered foam. Everything is running down, not just the distant universe in the unimaginable future. Right here, right now, the processes we call life, metabolism, thought, motion, they are all forms of entropy processing, all of them locally reducing disorder at the cost of globally increasing it, all of them participating in the same vast, irreversible flow toward equilibrium that will end, given enough time in the universal stillness of the heat death. This is not a counsel of despair. It is the opposite. The reason life is possible, the reason complex, organized, information processing structures like you can exist, is precisely because the universe is not yet at equilibrium. There is still an enormous thermodynamic gradient between the low entropy of stars and the high entropy of the cold night sky. Life exploits that gradient. It has been exploiting it for nearly 4 billion years on this planet. The gradient is still vast. The stars have not gone out yet. The party is not over. But it is a party that will eventually end. And knowing that it will end is not a reason to stop dancing. It is, if anything, a reason to dance more deliberately. What we do not know, the story of the universe's death for all its apparent completeness, rests on foundations that deserve scrutiny. There are things we do not know that matter enormously to how the story ends. We do not know the true nature of dark energy. The accelerating expansion of the universe is one of the most robustly observed facts in cosmology. But its cause, the energy that drives it, is entirely mysterious. We have measured its effect with extraordinary precision. We have almost no theoretical understanding of what it is, why it has the value it does, or whether that value will remain constant. The fate of the universe, heat death, big rip, big crunch, cyclic rebirth, depends entirely on the answer. We do not know whether protons decay. The consequences for the Degenerate Era are enormous. If protons are stable, black dwarfs and neutron stars potentially persist indefinitely, or at least for timescales so long that the distinction is moot. If protons decay on timescales predicted by grand unified theories, the remnants of all the universe's stars dissolve into lighter particles over periods of around 10 to the 40 years. Experiments continue to search for this decay. So far, nothing has been found. We do not know whether Hawking radiation is real. Hawking's derivation is widely trusted and deeply elegant, but it has never been directly confirmed by observation. If it is wrong, if some subtlety of quantum gravity changes the calculation in a fundamental way, then black holes may not evaporate. They may be genuinely permanent, and the black hole era may never end. The universe's long-term future changes entirely. We do not know whether the universe is genuinely heading toward maximum entropy, or whether some global property of its structure, its topology, its boundary conditions, its quantum state, prevents true equilibrium from being reached. Cosmologists generally assume that the heat death scenario follows from the known laws of thermodynamics, but applying thermodynamics to a universe of expanding space with dark energy and quantum gravity effects at late times is not straightforward. The assumption that equilibrium is reachable in an expanding universe is itself an assumption that deserves scrutiny. And we do not know what, if anything, happens after the heat death. Whether the long quantum silence of the Dark Era is truly the end of the story, or merely the longest chapter, or merely a condition from which some new beginning eventually emerges. This question sits beyond the current reach of physics. It may sit beyond the reach of physics permanently. The heat death, by definition, is a state in which nothing further happens, a state in which time has no arrow and events have no sequence. Whether time itself continues in any meaningful sense after the heat death is not a question the second law can answer. The warmth of now. Go back to the room. Listen again. The hum of the electrical device, the distant traffic, the creak of the building, the sound of someone somewhere doing something. You live in the warmth. Not just the physical warmth, though that too, the gentle 37 degrees of your own metabolism, the radiated heat of the objects around you, the sunlight that filtered through the atmosphere today and warmed the world outside, but the thermodynamic warmth, the astonishing, improbable, temporary condition of existing in a universe that has not yet reached equilibrium, a universe that still has gradients and differences and flows, a universe still doing things. The second law gives everything a direction. The stars burn in one direction. Time flows in one direction. Complexity emerges in one direction and eventually dissolves in the other. The universe had a beginning at extraordinary low entropy and is moving with absolute and patient inevitability toward the maximum entropy of the heat death. But the universe is not there yet. By any reasonable measure of cosmic time, even measuring in the currency of the vast eras we have explored, we are extraordinarily early. The Stelliferous Era, which will run for 100 trillion years, is barely a few % complete. The black hole era will dwarf it. The dark era will dwarf the black hole era. The heat death is not imminent. It is not close. It is not approaching on any time scale that should trouble you personally, or your civilization, or anything descended from your civilization for spans of time that the human mind cannot genuinely compass. What it is inevitable, or probably inevitable, or as close to certainly inevitable as anything in frontier science can claim to be. And there is, if you will let yourself feel it, something clarifying in that. Something that strips away the small irritations and the small preoccupations and the small anxieties that fill most days and replaces them briefly with a clearer sense of what is actually going on. What is actually going on is this. The universe began 13.8 billion years ago in a state of extraordinary low entropy. Since then, it has been flowing relentlessly and irreversibly toward the higher entropy states that thermodynamics demands. Along the way, in the warm, bright, energy-rich middle of that journey, it produced stars and planets and chemistry and life and minds capable of understanding the journey they are on. You are one of those minds. You are made of matter that was forged in stellar interiors and scattered by stellar deaths and assembled by 4 billion years of biological evolution into something capable of sitting in a room and thinking about entropy. You are, In the most literal and non-metaphorical sense possible, a temporary local reduction in the universe's entropy, a pocket of order in a flow toward disorder, maintained by the energy of a star, surrounded by the quiet and inevitable increase of entropy in everything around you. You will not last forever. The universe will not last forever. Nothing lasts forever, but the universe is not quiet yet, and neither are you. Listen to the room. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.